the December 7th edition of the IPNSIG Academy talks. Today's talk will be a discussion of standardization efforts for delay tolerant networking and interplanetary networking within the Internet Engineering Task Force. And our speaker will be Dr. Ed Birrane. He is a computer scientist and embedded software engineer who focuses on the adaptation of computer networking protocols for use in non-traditional environments. He has supported a variety of embedded software engineering efforts to include the NASA New Horizons mission, exploring the Pluto-Charon system, and the NASA Parker Solar Probe mission to observe the outer corona of the sun. He works with industry, government, and academia on the design and development of protocols to implement delay-tolerant networking architecture. He co-chairs the DTN working group within the Internet Engineering Task Force, where he is a co-author on the protocol version 7, RFC 9171, on the protocol security, BPSEC, RFC 9172, and the default security contexts for BPSEC, RFC 9173. He's a member of the principal professional staff at Johns Hopkins Applied Physics Laboratory as chief engineer for space constellations and networking. He's also an adjunct professor of computer science at both the University of Maryland, Baltimore County, and the Johns Hopkins University. Ed, if you're ready, please proceed.
Certainly. Just a quick note, reminder to attendees that this session is being video recorded.
All right. Scott, thank you so much for that introduction. As Scott mentioned, I do work with
recording in progress.
Thank you so much for that introduction. As Scott had mentioned, I do work with the IETF, the Internet Engineering Task Force, as we create standards for networking in a variety of environments. And of course, because this is the IPN, we're trying to sort of understand what is that overlap between standardizing things that work for our terrestrial internet, and where and how do we adapt those, and where do we need new things as we're trying to create networks different than the terrestrial internet, such as interplanetary networks. To try and understand how we've approached that question, the first thing we want to do is take a look at an interplanetary network from a network architecture point of view. And there are so many different considerations as to how we do this enormous engineering task. There are questions about governance, there are questions about finance, there are questions about physics and orbits. But if we were to look at this as a network and ask the question, for delay tolerant networking, what architectural elements do we need to take our sense of network services and make them work in environments where we don't have the traditional underlying comms infrastructure, and where we don't have that traditional underlying power infrastructure? What then would a network look like? And so that network point of view of an interplanetary network looks at things such as, how do we exchange data between endpoints? If we are on the internet, on the terrestrial internet, and we go to a website or perhaps even attend a webinar, we understand that the endpoints of those data exchanges exist all the time, and that there is a continuous, contemporaneous path that exists between them that we can always use. But that might not always be the case if we're trying to talk back to Earth from orbiters or landers. And so one of the things that we know we need in a network that will be an interplanetary network is the ability to tolerate cases where the end-to-end path does not exist all at once. So we do not assume that a path exists all at once. And if you don't assume that, then you want to look for what we call store and forward data exchange, where data will sort of hop or inchworm its way through the network. When it has a link, it can use it. And when it does not have a link, it can wait patiently for a link to come forward. And you never need that entire end-to-end to exist at once. If we then say end-to-end might mean waiting on an orbiter or waiting on a lander for an appropriate time, then we ask questions about security. How do we secure data when it is somehow in the network, but waiting for the next time that it can be transmitted within the network? And then we say, from a network management perspective, if we assume that we don't have an end-to-end, communication all the time, but we have to manage the network. How do we manage pieces or partitions of the network when they are on what we call the other side of the D, the other side of the delay, the other side of the disruption? And to do that, we need some level of autonomy in our network management that isn't always necessary in our terrestrial networks. And of course, if the idea of links coming and going over time is something that drives us to store and forward data exchange and autonomy in our network management, what that means is how we route data is also grounded in this idea of changing network topologies or time variant network topologies. So if we were to look at the interplanetary internet as a network, and the kinds of things that terrestrial networks do, there are things that make this look different. And because of store and forward data exchange, the unique nature of the security, network management, routing, and so on, we understand that we need to develop new things, new techniques, new protocols, and new technologies that would allow us to operate in these environments. I will just take a moment and point to the links in the bottom of this slide. When we talk about the interplanetary network aspirationally, we have visualized this in so many ways over the years. The top right visualization is sort of a standard understanding of point-to-point missions and a very mission-centric view of how we do communications. But if we then look at the bottom right, and these kinds of pictures have evolved over time, and if you are interested, please follow these links for the latest versions of these pictures as they evolve over time. But we really want to get to the point where we have something that looks like communications infrastructure across multiple space agencies to enable this kind of communication. But to get to that picture on the bottom right, we probably need these new kinds of networking features. Now, I say those kinds of new networking features, but what does that actually mean if you're a networking researcher and you're trying to standardize things to make these happen? Well, if we look at from the previous slide, data exchange, security, and network management, we can talk about the capabilities that are important to us. We want to be able to send data without knowing if the destination that we're sending to is online or not. Because if it's not online, and we have, for example, store and forward transport, then we know that something in the network will hold on to this data until our destination comes online, obviously within reason to prevent congestion. We understand that retransmissions don't have to start from the beginning. On the terrestrial internet, if the network stops, we have to start all over again. How many times have we gone to a website and something was spinning and we weren't making that HTTPS connection and we just stopped and hit refresh and started all over again? Well, if that data exchange hangs in some way from a lander going all the way back to Earth in the middle at some orbiter or relay or trunk line, you don't want to start all over again from the lander with that retransmission. In fact, that lander may have transmitted the data into a reliable interplanetary network with the assumption that the network may hold on to it, so the lander could reclaim some storage and go about its next set of observations. So retransmissions don't always have to go all the way back to the beginning. If you then assume that you don't have end-to-end connectivity and therefore not what we would call sessions and session establishment as we would do on the, for example, terrestrial internet, then you may need to add annotative data with each of your individual packets or bundles or data items in the network, because you can't assume that those endpoints, which may or may not be online at the same time, have a common understanding of a session or the semantics around that data exchange. So when we start looking at the kind of features that we want, there are some terrestrial analogs to this. And in particular, people often will point to text messaging or email. When we get off an airplane and come out of airplane mode and we reconnect to our cellular carrier, and suddenly we get all of the text messages that were destined for us, but couldn't be delivered until our phone was back on the network. Or email, which is a much more common and longer-lived example, where we will bring up our email client and collect all of the email from some exchange server, for example, as we are trying to synchronize back up with what's going on. So we understand those features as applications for text messaging and as applications for emails, but Text messaging applications are custom built for that purpose. Email clients are custom built, or email servers are custom built for that purpose. What we want to do with IPN and in the networking architecture is to take those common capabilities and not recreate them in different applications at the application layer, but say this is a standard solution to what is going to become a standard problem. And if we're able to do that, and standardize protocols that explain how to do this kind of delivery, then every application that would sit on top of this, messaging, email, and space applications, would all get these benefits, and they would all get them in the same way with the same behavior. And something that you'll hear me say at least one more time in this presentation, and then in general, the observation of making a true international interplanetary network is going to be based on standards, not stovepipes. A common agreement of how we share data, and a common agreement on how we should behave when we receive data and how we should behave when we don't receive data. If we then look at that from a standards perspective and we say, where do we standardize things? For the context of this talk, there are two significant standards organizations. In the world, there are way more than two significant standards organizations. But just for our talk, the two that we're focused on here is the Internet Engineering Task Force, the IETF, and the Consultative Committee for Space Data Systems, or the CCSDS. The Internet Engineering Task Force, which should not be a surprise, is focused on standardizing things for the Internet. And the Consultative Committee for Space Data Systems, which should be no surprise, is focused on standardizing things for space. Both of these are large organizations. Both of these decompose their organizations into areas and technical areas. In the IETF, we have routing and internetworking and operations and management, routing, security, and transport. In the CCSDS, we have systems engineering, mission support, cross support between missions, things on board the spacecraft, space links, and space networking. Generally speaking, the IETF has a great experience in the internet service provider, vendors show up, Internet of Things, mobile ad hoc networks. All of those are represented and evolving in the IETF. Typically, those meetings are attended by roughly 1,500 people or so. I think the last one, IETF 115, which occurred in London just last month, had about 1,500 attendees, both combined face-to-face and online. And they meet exactly 3 times a year. And it's really open to anyone that is interested in these capabilities. You can sign up, you can pay a registration fee, you can show up, it's okay. The CCSDS is a little more moderated. It has deep and knowledgeable expertise in space mission development and operations. It has hundreds of attendees, and they meet twice a year. And to show up at the CCSDS, you are doing so under the auspices of a national space agency, such as NASA or ESA or JAXA or so on. And this is 2 different approaches to the problem. The IETF is everyone can come and talk about computer networking, and the CCSDS, it is also people who are there under the auspices of a space agency and can speak specifically to the unique nature of space systems. Now, the question becomes, as we're building the interplanetary internet and the standards therein, where do we go to standardize this kind of information? How do we look at the expertise from these 2 communities and understand what is the best combination here? And that is something that we have struggled with over the past really 10 years of much of this work. So in order to start addressing that, let me give you 2 observations. The first is, if we look at the interplanetary network as a series of features, and we've talked about them already as store and forward data and end-to-end security and autonomy in our network management and how we do time variant topology management, well, those are all important things. And if we're building a solar system internet, looking at this graphic, the picture on the left, and we have landers on some surface and orbiters going over them and some sort of relay spacecraft or trunk line back to Earth in some way, that is local data collection, regional aggregation, and some sort of backhaul. But if we were to really redraw that picture in just a minor way, and the picture on the right, and say something is much closer to Earth is local terrestrial sensor networks, buoys in the ocean, or small items in buildings, and data mules, which are doing regional collection of that data and aggregating it in some way, and perhaps even exfiltration nodes where we have things that are flying overhead to collect data as we go, to include LEO satellites. then these two pictures from a networking standpoint do not look dramatically different. Obviously, the individual features and platforms and environments are dramatically different. But if we're talking about networking features, a solution to the thing on the left might also be a solution to the thing on the right. The other observation that we make, if we look at delay tolerant networking and this idea of maybe storing and forwarding data through the network, that we know we need that at the interplanetary scales, at astronomical scales. But what happens if we have those same problems closer to home? And do we have those same problems closer to home? And a claim is that, yes, we do. Modern networks encounter problems similar to the high delays and the frequent disruptions that DTN was built to solve. And the IPN aspirations for interplanetary networking does need DTN for these same purposes. How do we defend that claim? Well, one thing we can do is look at what is really useful on the internet today. The internet, as it operates today, functions fundamentally differently than the way the internet operated at the turn of the century, right? Today, we have content delivery networks, which is caching and storing and placing data throughout the country and throughout the world so that not all of the users of that data have to come all the way back to the source to understand how to get it. We have data subscriptions and push mechanisms to try and reduce chatter on pull mechanisms. We have gone in data centers, a lot of autonomic computing so that we have rules and automation, and to get away from putting all of our data back to a single place to operate on it. And something that has become incredibly important to the modern internet are essentially stateless data exchanges and RESTful interfaces. And all of these are network approaches that we see in some way in the overall design of DTN protocols. So we know that the existing terrestrial internet has evolved to have similar features. And why do we do that? Well, because if you assume that you have infinite bandwidth, well, that leads to problems. To sort of tip my hand on the answer to that, all of them are congestion. But if you're waiting for an end-to-end path to show up, as we look at on this picture to the right, on the top version of that figure, if we have nodes 1, 2, 3, and 4, and we're having these periods in the shaded area of connectivity between two nodes. So early on, node 1 can talk to node 2, and later node 2 can talk to node 4, and then much later, node 1 can talk all the way to node 4. Well, that's fine to know that in advance, but what do you do with that information? If your network can only wait for the end-to-end path to exist all at once, then it's storing that data for a long time. And when that end-to-end path comes up, maybe there are other data volumes that need to be transmitted. Data volume D1 and data volume D2 suddenly are competing, whereas in a store and forward approach, which would be the picture that we're showing on the bottom right, if a data volume shows up and there's a link that gets you just a little bit of the way there, and you can get off node 1 to node 2, and then you wait a little bit at node 2, and then there's another link that comes up and you can get off node 2 to node 4. Well, you can gradually, incrementally get through the network and not wait on that end-to-end link, so that later, when there is luckily an end-to-end link, some other data can go through instead, and not everyone is fighting for the same ideal resource or ideal condition. So waiting for end-to-end paths can cause congestion. Sending traffic as soon as possible can cause congestion if you don't wait for the right time to send it. Handling congestion in a network by dropping the data causes congestion, because if you take data that someone has sent you and you're in the middle of the network and you decide to throw it away because the network is busy, what's going to happen to the original sender of that data? In many cases, the original sender of that data will say, I never got an acknowledgement for this data. I have timed out, and I'm going to generate it and send it again. And if you generate it and send it again, and it gets partway through the network and hits congestion and then gets thrown away, it might happen again. And at some point, you're just creating and pushing data in the upstream part of the network just to throw it away later. And that actually all by itself can generate congestion. So what we've learned from this, we've learned the evolution of the terrestrial internet, we've learned from analyzing this interplanetary networking problem, is that even small changes to how we deal with transport can have really meaningful impacts on what it means to get data end to end. And one of the ways to look at this is to say, what is the right time to put data into our network? And we will talk about that in just a little bit. Between this past slide and this slide, what we are coming to understand is, from a networking point of view, there are things in the delay tolerant networking suite and the aspirations and the vision of interplanetary networking at large that are absolutely necessary for astronomical data exchange, but also were much more useful, or as useful, closer to home and on Earth. So with that observation, we can come back and say, where do we want to standardize this? Interplanetary networking is a series of networking features that are absolutely needed by both the CCSDS in space and also on the internet, for the kinds of ways that we're going to evolve the internet to work as we push the terrestrial internet into more and more challenged and remote environments. So how do we mix these development cultures, these technical experiences, and how do we share this expertise? And certainly one way to do that, and the way that we're doing that for some parts of the DTN suite, is to build working groups in both the IETF and the CCSDS. Have in the couple of examples that I'm going to talk through today, have the IETF do standards and have the CC and do standards for all comers that want this type of networking. And then have the CCSDS working closely with the IETF, customize those in what's called a profile, to profile those internet standards for what is needed in the space environment. And we feel that that is a good overlap and a blend. So if you were to attend IETF meetings and you were to go into the transport area, there is a DTN working group there. I co-chair that working group. If you were to then go to the CCSDS in the space internetworking area, there's a DTN working group there as well. And these working groups do not duplicate effort. There are people who attend both of those working group meetings. The chair of the CCSDS working group and the chairs of the IETF working group meet regularly. And this is a positive and collaborative environment for both organizations and the agencies that support them. However, this talk is called IETF. So given that as some background, let's dive a little bit more into the IETF specifically. And I know that there are going to be later talks in this same lecture series for the CCSDS. So if you are unfamiliar with the IETF, the Internet Engineering Task Force, the first thing I want to say is that all of the material that you're going to see here from the IETF perspective is available openly and online. There are many links in this presentation, and to be perfectly honest, you're also able to Google just about anything and have it come up. It's pretty easy once you understand the mechanisms of IETF, as I'm going to go over them today, to find what you need to within this organization. But let's start with the mission statement for the IETF. It is quite simple. It's a great mission statement. The overall goal of the Internet Engineering Task Force is to make the internet work better. That is the rubric. We have to understand everywhere that the internet is going to go, we have to make it work. We are the engineering task force to keep this capability running. The internet, terrestrial internet, near-Earth internet, interplanetary internet, this is the greatest communication mechanism that we have ever created as a species. And we have thousands of people working all the time to keep this evolving and going as our needs and technologies evolve and go. If we add, make the internet work better anywhere in the universe and not just on Earth, all the better. It is that end-to-end vision of from my desktop, from my cell phone, through a cellular carrier, to a packet switch network, up to a spacecraft and back again. If that's what the internet becomes, then that is a good thing, and we have to make it work. Within that mission, the IETF is a technical organization. We produce high-quality, relevant technical and engineering documents. The underlying emphasis is mine, that influence the way people design and use and manage the internet in better ways. An example of this free thinking and open-ended thinking, particularly to anywhere in the universe as we go up in altitude a little bit, is the picture on the right, which is from the IETF Twitter feed, where at IETF 115, which was again in London this past month, where Cisco came and presented a project talking about how we could use WebRTC for Leo constellation. So there is a lot of focus right now in trying to understand, in the very near Earth case, how do we tech transfer existing internet technologies that work in near altitudes, right? Low Earth orbits, medium Earth orbits. The question is, that really puts a strain on what these algorithms were built to do. How do they then work if we go into high altitudes, geosynchronous, cislunar, and beyond? The other way of talking about the IETF beyond its mission statement is to say, how does the IETF operate at all? So there are a couple of principles of the IETF, and I want to just list them here and then in a moment emphasize a couple of them. The first and really foremost principle of the IETF is that it is an open process. All of these, by the way, are summarized from ietf.org/about/introduction, and you can see all of the text there. But my summary of these, when they say open process, any interested person can participate in the work, know what is being decided, and make your voice heard on an issue. It is open. You are free to join, minus registration fees. You are free to show up at any of the working groups in person or online, join that queue, and express an opinion. So it is important that this is open, because the only way that we keep something like the internet going, and the only way we make it work better, is to continue to elicit and understand and fuse incredibly diverse opinions. Because even on Earth, this process and this engineering feat is enormously complicated. Packets don't care about groupthink. They care about the right answer. The technical competence is right behind that. The IETF is willing to listen to any technically competent input from any source. ... We expect IETF output to be designed to sound network engineering principles. So not only can anyone join, but also anyone that has good, solid technical input can make a difference. It is a volunteer group. What that means is the IETF does not pay people to participate. You come either on your own, or you come because you are being sponsored by an organization to send you there. How do we make decisions then? If anyone can show up and there's a focus on technical and sound network engineering principles, obviously in those cases there will be disagreements. And what do we do about that? Well, we come back and say, the way that the IETF works is rough consensus and running code. If you were to go to an IETF meeting and simply come back and say to anyone that's walking by, rough consensus and running code, they would look right back and say, absolutely. And then the last bit is that protocol ownership. When the IETF publishes a protocol, when it takes ownership of a protocol, it accepts responsibility for every part of that protocol, even the bits that may or may not always be the most interesting parts. It is a whole ownership, because that's what sound engineering principles are. And the things I think are really, really important to focus on here as we go into this next phase of very difficult discussions on how do we do this enormous engineering and networking feat of a solar system or an interplanetary network. We need an open process. We need diverse opinions. We need diverse skill sets. We need people that have operated different types of networks, space networks and non-space networks, well-resourced networks and ad hoc networks. And the technical competence. We must be willing to listen to any technically competent input, but at the same time, we must focus on solutions for everyone. But I said earlier in this talk, it is standards, not stovepipes. Something that happens very frequently in any standards organization, and the IETF is no different, is for someone to come in and say, my company, my business, my university has built something and we like it just the way it is, and we bring it to you whole cloth so that you can standardize it with no changes. I can tell you how that goes. And the answer to that is rarely does an individual organization or an individual point of view come with a complete solution that is a technical solution for everyone. So part of technical competence and being willing to listen to that input is to have your own input heard, but also to listen to the input of all of the other people that are participating in that open process. There is less on, here is my tool, go make it a standard, and there is more of, here is my contribution, how do we make sure this works for everybody? So how do we make sure this works for everybody? for DTN, which are the network architectures and then the individual pieces that we need for interplanetary networking. So when we talked about where does the DTN live in the IETF, I said before, it is a transport concern. How do we get data from one end to another? It lives within the transport area, and there is a DTN working group. A little history on that. Originally, there was not a DTN working group in the IETF, the Internet Engineering Task Force. Back in 2002, 20 years ago, the Delay Tolerant Networking Research Group was formed from a different organization called the IRTF, the Internet Research Task Force. And the Internet Research Task Force is to go look at new and emerging and very strange and important ideas to understand what we want to engineer. And so the original DTN RG, whose work has now concluded, was this observation that a non-interactive, asynchronous form of messaging service able to operate over these diverse kinds of networks would be useful for a lot of people. And they produced 14 RFCs, requests for comments, which are the mechanisms by which IRTF and IETF publish. Things such as RFC 4838, a somewhat famous document, which is the overall DTN architecture out of the IRTF Bundle Protocol version 6, RFC 5050, an original security protocol for Bundle Protocol version 6, 6257, a TCP convergence layer, and so on. When the research working group had hit sort of a critical mass of understanding of how all of this might work together, then there was a discussion that says, are we still doing research, or is it time now to switch this from a research project to an engineering project? And at that point, in 2014, after 12 years of doing the research job, the IETF came together and said, it is now time to make this an engineering effort so that in the Internet Engineering Task Force, a DTN working group, not a DTN research group, should now pick things up. Originally, those major work items from the D10WG in 2014 were to take the outputs of the research group and put them through an engineering standards process. And if I go back one and say an engineering standards process is willing to listen to technically competent input and being able to make sure that we build a solution that works for all and all of our internet users that need all of these networking features. And to date, we have produced 4 RFCs. 9171, which is Bundle Protocol version 7, 9172, which is a security set of extensions for BPv7, some security context to say how you might use this security on the terrestrial internet, which may be different than how you would use the security in an interplanetary internet. And then a way of putting this on top of TCP, which is an important consideration for the terrestrial internet. We are also looking at additional work related to security, and we have just now completed with these first 4 RFCs in February, I believe, of this year. We finished that work, and now we rechartered and said, what are we looking at going forward? And what we're looking at going forward are now the things that will help us start to build and manage and operate these initial delay tolerant networks. So there are 3 major parts of the new work being undertaken by the DTN working group in the IETF. The first is naming, addressing, and forwarding. We understand that IPv4 addresses all by themselves are not enough, which is why we have network address translation, which is why in our homes, all of us have 192.168 addresses, and then different addresses as we go through our home service providers, Verizon or AT&T or so on. When we start looking at how does this scale to billions of small devices as we look into IoT and mobile ad hoc networking, as we look at tens of thousands of spacecraft, and not just in one LEO constellation, but in all of the LEO constellations that are being considered. How does this then extend from an addressing and a naming point of view to cislunar space and interplanetary space? When we look at all of this, the IETF is starting to understand the hierarchical naming schemes and approaches that can be used for everyone. And then at that point, for example, a great handoff to organizations like the CCSDS to say, here's a hierarchy, here's something that we know will scale based on our experience with the terrestrial internet. Now, how would you adapt pieces of this for addressing in space at Mars and cislunar, separate from how we would address things terrestrially? But again, it is that common architecture for the assignment of names, for the late binding of names, for forwarding of BPv7 bundles. That common architecture is coming out of the IETF, and then the specialization of it or the adaptation of it or the use of it for space systems would come out of the other organization, the CCSDS. Another important one, and if you go back to one of the early slides, the initial slides in this talk, we talked about autonomous network management. So how do we understand what that means for a DTN in a space system? Operations, administration, and management. It's a very important topic, and I have one more slide on that in just a moment. And then we are still extending some of these existing protocols as we look at quality of service, as we try and understand how we continue to adapt and use more and newer cipher suites and security approaches. How do we signal that custody transfer approach where we say information might need to inchworm its way through the network? So if I'm a node in the middle of the network and I get a bundle, I can go back to that original sender and say, I've got this bundle from here on out. You don't need to worry about retransmitting anymore. How do we signal that? So things of that nature. If I do a little bit of a deep dive on just one of these many topics, the network management piece is one that I'm personally excited about. When we talk about what does it mean to manage a DTN where some of the nodes you're trying to manage, you might not talk to for minutes, hours, days, or weeks. How do you manage without any closed loop control? How do you manage when you have periods of disconnectivity, when you're relying on autonomy? And autonomy might mean automation because sometimes it has to be deterministic. How do we reduce to the fewest dependencies possible? We can't take a small sensor sat orbiting Mars and ask it to fly the same very heavyweight stacks that we run in our terrestrial data centers. How do we get very concise encodings? So one of the items being looked at in the DTN working group now are architectures like the things on the right, where you have managing devices and managed devices that communicate, but they communicate to configure themselves for how they will operate in the future with autonomy agents. In the picture on the bottom right, where you have autonomy engines on a managed device that are performing autonomy actions and self-management based on expert systems and deterministic rules that can run at very high rates, hundreds and maybe even thousands of hertz, decision trees. If you're interested in any of that, operations and management, naming and addressing, the autonomy piece, the security piece, or any of the other things that are coming up in the IETF, the next question is, how can I get involved? And because the IETF is such an open organization, there are really a lot of good ways to do that. The first is go review the online materials. The DTN working group in the IETF has a public open homepage, and that, like many other things on the IETF, is housed on something called the data tracker. The datatracker.ietf.org is where all of the data associated with IETF materials and working groups lives. And the place where the DTN working group stuff lives is datatracker.ietf.org/WG for working groups/DTN. Every meeting of the IETF is recorded and placed on YouTube. So, for example, if you wanted to look at meetings from IETF 114 or 115, go to YouTube and search IETF 115 DTN, and you'll hit that link. And here is the link from the latest one. I found that link on YouTube by typing IETF 115 DTN. There's a screenshot on the right of someone presenting exactly that network management work that we had just presented. I just talked about on the prior slide. Every working group has a mailing list, and that mailing list has a homepage. So there is a DTN IETF mailing list, and it is particularly recently been fairly active. You can join that. Anyone can join. Anyone can subscribe. Even if you've never come to an IETF meeting, even if you will never attend an IETF meeting, you can go to this website, subscribe, view the archives online, and participate and make your voice heard. And then lastly, of course, always you can attend a meeting. Virtual attendance is supported. The next one is coming up in March in IETF in Yokohama. And you can attend and get all the information you need there by going to IETF.org. Now, we've talked a little bit about the IETF. We've talked a little bit about the DTN. I've got just 2 slides remaining in this roughly 40-minute presentation. There's another piece of, I think, very, very interesting work that I think will have some applicability to what we talk about in the IPN, and that's this idea of time variant routing. And the idea becomes, what happens when we know that our network topology is changing? And if we know that our network topology is changing, what do we do about it? On the terrestrial internet, if a link goes down, there's a reaction to that. Sometimes that reaction is quite panicky. Sometimes the reaction is, holy smokes, the link just went down, panic and broadcast and try and reestablish that link. And it is an absolute error condition until that link comes back. Well, in an interplanetary network, we have links coming and going all the time. We cannot react to the loss of a link as if it was an error condition. For us, the loss of a link is not the exception, it is the rule. So when we propose this to the routing area, that there is thinking associated with how to deal with these dynamic changing topologies, the routing area director said, well, you know, we actually have this same problem for other things as well. If there are devices that don't want to transmit and power their radios unless they know they have enough data to make the transmission worthwhile because they're battery operated or solar powered, and they could literally last longer in the day, if they're solar powered, for example, by transmitting less and strategically. Or if you have nodes that are transmitting using cellular data and you have the idea of on and off peak minutes, and if you transmit too much during busy times of the day, you may pay more. So maybe you take certain data and hold on to it and transmit it later in the day, whether you're the source or whether you're an intermediate node. Or, and something that's becoming very important in the IETF, or important to the IETF, is the idea of ecologically friendly computing, green computing, computing that uses less resources and less power and is trying to be more efficient. And again, for example, to use more power at times of the day where the cost, either the social cost, the environmental cost, or the actual cost of power is less than it is at other times of the day. So the way a working group is formed in the IETF is to create something called a birds of a feather meeting, or a BOF for birds of a feather. And in that BOF, we get together and we describe problems, not solutions. And we gauge the community's expertise and interest to see if those are problems we want to solve. So at IETF 115, we had a BOF for time variant routing in our routing area. Again, like any other working group meeting, BOF meetings are also recorded and published on YouTube. Here is the link to the YouTube BOF attendance. It was about a 2-hour meeting. We had 135 attendees. Roughly 70 people stood up affirmatively and said this needs to be a working group and we would support it. And this is really important for us. About 5 said no. A 70 yes, 5 no. That's pretty good rough consensus. We don't have running code yet, but that's pretty good rough consensus. Then perhaps this will then by IETF 116 turn into a time variant routing working group. And that's important because a time variant routing working group, to reason about this, is a working group staffed with the people that build the routing algorithms that make the internet run. And that is a wealth of expertise that we need. So in conclusion, there are really 3 things that I hope you take away from this talk. The first and foremost is an interplanetary internet is a tremendous, tremendous endeavor. The aspiration is something that I think is societally impactful, as our terrestrial network will be as we continue to instrument and grow into our solar system. And we've always heard space is hard, and we know space is hard. We rarely get it right the first time around, but also networking is hard. The terrestrial network in the most beneficial of conditions with the infrastructure that we have still takes just tens of thousands of people and billions of dollars worldwide, trillions perhaps, to run and run well. Networking is hard, and blending these technical knowledge communities is hard. So we have to accept that we are doing something that is, pardon the pun, astronomically difficult. But the other observation here is that the way that we go forward is we need standards, not stovepipes. And when we talk about standards here, we understand that a standard is an entire set of information, not picking and choosing just the pieces that work for you and not the pieces that work for someone else. And why is that? Because networks are built from networking devices. If you want a network, you don't go to the networking store and buy a network and go home and put the network in your house. You buy devices, you buy routers, you buy switches, and you configure them to talk to one another. And this thing that we call a network is just this emergent behavior of all of these individual devices choosing to talk to one another. And so if you look at a network and the functions and features of a network, as the functions and features of the networking devices, because those are the physical things, the network is just a logical idea, then you realize that if you're a spacecraft and you want to participate in a network, then you're really a networking device. And you have to then choose to be a networking device and choose to support the features and the standards and the whole standards that make you a networking device, because that's the only way that we get a network. And in the last and really important thing, and probably the most important thing from the entire presentation here, is that this future thing that we want to build is something that we're going to create together, is something that you're going to create based on your expertise and making your contribution heard and your voice heard. And we need you to contribute, and we need your ideas. And there are many ways to do this, right? I mean, obviously, one is joining the IPNSIG is an excellent way to start this. Joining the IETF is another. And then if you're struggling with the way to truly make that technical expertise heard, to come and help solve this astronomical problem, find a way to find me and we can talk about it. And with that, I think we are at the end of this talk.
Great. Thank you, Ed, for this very thoughtful and thought-provoking discussion of the standardization efforts for in planetary networking in IETF and beyond. We have a small number of questions pending, and I think we've got actually plenty of time for that. The first is a question from Klaus Mogren. He asks, is there an easy way to run a DTN node yourself at home or in the cloud and make it publicly available for routing? He says he's done some work with DTN Go, but not with other implementations. And the question is, if you've got any hints on how we might go about setting up a DTN node that takes part in a network.
So the immediate response is, that's wonderful to hear that people are going into onto the terrestrial internet and looking for these implementations. And DTN Go is one of them. And once BPv7 was standardized, we started to see many implementations come forward, some which have been around for a long time and adopted to BPv7, and others which have come on since the standardization of BPv7. As a working group chair, my very first intuition is to say, that's a great question. Let's take it to the mailing list. And I'll say that again here, and only slightly in jest, but it is, if we want to build a bundle protocol network where we know people are producing bundles and consuming bundles, and they want people to route bundles, and they need the help to make sure we build up that infrastructure, that is just emerging now. And if you think about it, how could it not be just emerging now? Because we just standardized BPv7 really less than a year ago for people to start building out. But we do have companies and individual users that are building BP networks that would be open to anyone helping be a node and supporting in that way. So I don't want to be a bottleneck to that information. What I would suggest is, go find that link from the prior slide, go to the DTN mailing list and join and say, hi, I have this infrastructure. Who else is thinking like me on this? And who needs some extra compute resources so that we can start doing this kind of research? The second part of that is, there are a large number of research and closed networks that are using bundles for research and using bundles for operation. They're a little less interested in having unknowns in a closed network come in and start routing and handling their traffic. But I do know that many of those folks are also on the mailing list. And so getting that question in front of that community would be an excellent first step.
And I have one thing to add here, which has come up. Several people in the chat have contributed this. There is a projects working group of the IPN special interest group that is engaged in really just this sort of thing. And as far as I know, it's open to anyone who wants to contribute. So I would say, if that looks like a promising avenue for you, then go to the IPNSIG website, look for the links to the projects working group, PWG, and try to participate in that way. The next question that I've got here is from Juan Freyer, who says, thanks for the excellent talk. He wants to ask about challenges that you foresee, both technical and non-technical. What are the most relevant long-term risks that you identify in interplanetary network?
That's a wonderful question, and a very, very difficult question, because this is, as I said before, as a technological endeavor all by itself, this is such a hard problem. Space is hard and networking is hard. The one thing that I think is a technical, there are two real technical challenges that are in front of us today, and I will talk to them because those are the ones that are in front of us from an IETF perspective. And the first is this idea of naming and addressing and getting data back and forth in a time variant topology. There's a tremendous amount of research associated with it. There are a lot of really good ideas, and we do have some operating systems. But when we look at true scale of thousands and thousands of organizations, growing to thousands and then into millions and then into many millions, perhaps over time, with both virtual and physical nodes, how do we make sure that the naming and the routing of that remains scalable? Time variant and scalable become extremely hard challenges. And we do have some good ideas on that. And that's one of the reasons, and again, my perspective here is focused on the IETF for this talk, is why that is one of the charter items for the recharter of the IETF, is to really focus on that system that works for all. The other is the autonomy in the network management. For a DTN, if we accept that we don't have closed loop control and we want more autonomy, but deterministic autonomy deeper into the network so that nodes can manage themselves, we've got good ideas there, and we will have standards coming out for that. But the transitioning that into operational use and understanding how we manage in an open loop fashion is something that's going to be very, very different for some of the other both space systems and terrestrial data system data center management that we've had in the past. So I think those are two technical concerns. The other non-technical concern is governance. And what does governance mean? If we look at governance in networking or in other areas today, typically it's based on some kind of jurisdiction, and typically that jurisdiction is based on geopolitical boundaries. We might say that the internet might have to remove certain search results or remove certain kind of content in one country versus another based on some kind of governance or understanding of the laws of that country. What happens when we build this out into the solar system and into interplanetary scale, where there's not that same sense of jurisdiction? And what does it mean to govern and enforce those individual rules? How do we do that? And we have the mechanisms and the tools and the technologies to govern in a variety of ways. But what we need to understand is, how should we govern? And I think that is going to be an important non-technical consideration, which I also know that the IPNSIG is looking at and creating statements on. And just an apology on the go back. Of course, the IPN projects group would be, probably of all of this, the best starting place to say, how can I contribute with my DTN nodes?
Great. Thanks for that. And one more question we've got in the Q&A. This is from Maria Inés Robles, who asks, are there guidelines or other information available on network characteristics from different missions? It'd be important to be able to simulate mission conditions in lab work so that mission-ready protocols for the Moon and Mars can be developed.
Absolutely. Many universities have looked at and published on what would be good networking features to have and how to simulate. There have been, just in the realm of DTN, there have been simulators, networking simulators built specifically for DTN. I believe the one is called the One, right? The One simulator. And as these protocols have matured over the years, their support in different network simulators has grown. There is something called the Trek resource kit as well, which is an openly available kit provided, I believe, by MITRE Corporation. which would give a DTN installation in a network simulator that would simulate some interplanetary networks out of the box with some kind of delays and so on built into the simulation itself, based on what we think is sort of realistic. So there are some mod sim things for sure. And then I know there are a significant number of publications on what these things look like. So I think some literature review would find some good hits. And then this would be another area where, from an IETF perspective, the focus is on the internet at large. But when we really focus in on where is that expertise for space systems, the members who are also in the CCSDS and are looking at this from a space mission perspective and what we think we need feature-wise there, and the architectures that are coming out of the CCSDS for this area, is another good place. And then, of course, the IPNSIG is also producing materials like this. So I think the best way to engage here is to go find the mailing lists associated with this. I have the link for the IETF one, to come in and post these kinds of questions. Not every working group is well, what I can say is that the DTN working group is a very friendly working group, and it's there to make sure that we understand how all of these technologies can be infused. So it would also be a good question, again, to post in that mailing list, and also to post back to the IPNSIG itself.
Great, thank you. We're just about out of time. I will mention that Keith Scott reminds us that actually the TREC system is a NASA product that's accessible from Marshall Space Flight Center, but you have to have some sort of a licensing thing with them to do it. There's no cost, but you have to arrange with Marshall. The product from MITRE that's very useful for this kind of thing is the DTN Dev Kit, which can be accessed from the NASA DTN web pages. And I don't have a link handy, but I'm sure we can find one. And I believe that is the end of our questions and just about the end of our time. So could I ask you to move ahead to the terminating slides of the presentation here. We've got several other IPNSIG Academy keynote talks lined up over the next 6 months or so. This is a list going back to the very beginning, starting in this past May, and there will be notifications going out to the IPNSIG mailing list for these as they come into view. They're on a essentially monthly cadence, and a number of additional topics are being considered for scheduling beyond April. So there's lots to learn about this stuff and lots to talk about. Next slide, please. This is information about joining the IPNSIG. Many people already have. We've got something over 900 members today, and from all over the world. Everyone is welcome to join, listen, contribute, and help out with some of our working groups. And I think maybe that's one more slide, I think, is probably the end. Yeah, we're at the end now. There will be a survey. Please tell us what you thought about this talk, and anything else any other comments on interplanetary networking or the IPNSIG that are on your mind. We're happy to learn something new. With that, I believe we are concluding for today. Thank you all very much for sticking with us. Thank you particularly to Ed for a very compelling and interesting talk. There are great ideas in here. And at that point, we'll stop and see you maybe next month. Thank you.
Thank you.